This is a fascinating post by Eleanor. She shows a diagram, a GIF image of some seismic events underneath Hawaiian volcanoes. So I just want to provide some commentary on this because these things look a lot like mineral deposits. Here we're looking at like 40 kilometers down, so I didn't really expect seismic activity to be happening at that depth, but anyway, let's see what it looks like. I just converted this into video so I can actually go backwards and forwards, and you can clearly see that these seismic events are happening in, well, you can identify the planar continuities, right, if you look at it sideways like this. But another thing that's interesting is that these have linear geometries to it. So these are triaxial shapes. So if you rotate it around, you can clearly see that they are more elongated in this direction. So they are more prolate than oblate, which is kind of interesting. There's a couple of axial symmetries in here, but I'll show you the most obvious one, which is this one here. And that is probably some sort of pre-existing fabric. And if you rotate it around and tilt it, it's going to be more tube-like, so prolate. And that prolate, overall prolate shape of the seismic activity is plunging in the same direction as these small zones of seismic activity. Yeah. So these smaller zones. So they're coaxial. So the larger enveloping surface is coaxial with these smaller ones. Okay, so I tried to reverse engineer this and put it into 3D points, which I wasn't successful. I had an argument with ChatGPT, wouldn't listen to me. So it's kind of like did a really bad job of it. But anyway, this kind of illustrates the point. If I look down on it, it has a elongation in that direction. So, but if you look at it sideways and look at these planar zones, they are planar, but also linear. And if you look down the overall plunge of the system, it looks round and elongated. So therefore, this is a prolate object. But within it, you have oblate continuities as well, but I think in the video they're more like triaxial. So they have definite linear continuities. So that's really interesting. What's so interesting about this to me is that when you look at it this way, there is a bounding area. I'm not sure if that's the bounding area of where they've taken the survey. I have no idea, but it could be an actual geological feature. Commonly you find these features, for example, in anticlinal closures, and these geometries at least, in mineral deposits. And yeah, so yeah, it's really interesting how sort of similar these shapes are. So if you look at the planar continuity, I can analyze for the planar continuity here and plot that on a steering net. They look like this. That is a concentration of the poles of the seismic points locally. So determined planar orientations. That's very planar. But then you have, if you plot the linear component, then it plunges a consistent way, or it actually peaks along a certain direction. And that's in that direction there. So if you rotate it around, overall, that's the linear direction. So that's the geometry of this seismic swarm. So Yeah, really interesting. Another thing to note is that you can see these vague sort of zones that are vertical, and which has a different axial symmetry to the overall system. And this one here is hemming in seismic activity on one side. So I mean, I would even see that as a Perkins discontinuity here there. And you can see local seismic activity that are parallel to this orientation, which is completely different from everything else. Very interesting. So this sort of nested architecture that you see in these seismic points is very much like what you see in mineral deposits. You have first order enveloping geometry, and then you have internal continuities that, say, resource geologists are interested in, but they rarely ever look at the boundaries of them. So yeah, as a structural geologist, this is absolutely fascinating. So thank you very much, Elena.